Okay, so let's take a quick look at the Laplace transform. Also, we like to build up a small table and then work our way to some example of solving an ODE using the Laplace transform. So let's start with the definition of the Laplace transform. First, if we take the Laplace transform, this is typically how it's written, of some function in time, we have the improper integral, so we integrate from 0 to infinity, and you think that any area that runs out, any function that runs out to infinity, you think that the area will go infinite, but of course we end up taking the integral of functions that we know to converge, and this e to the minus st of course helps because it decays rapidly times some function in time dt, and since we're integrating with respect to time, we should be left with something in terms of s. Since I'm taking the exponential of an s times t, if t is measured in, say, seconds, then since I can only take the exponential of a whole number with no units, then s must be measured in per seconds, which is a frequency, or hertz. So this seems to transform some function in time into some function in s, which we've established as maybe some frequency, again measured in hertz. So this is the basic definition, and let's start off with an example where we'll just take the Laplace transform of the constant function 1. We can put in any constant c, but we'll generalize maybe after this. So let's use our definition. So our function in time is just 1. And we get e to the minus st here. We just plug in 1 dt. So we end up just integrating e to the minus st with respect to time. And so if I integrate e to the minus st, well, since this is an improper integral, let's just write this the way we know to write it. Let's just choose some dummy variable, let's say j, and let's let j run out to infinity, and we'll integrate from 0 to j e to the minus st, say dt. And so we'll take some area, hopefully that goes to 0, and let's say we'll start from 0 and then we'll go to some point j, and then we'll just push j on out to infinity. Alright, so if we integrate e to the minus st, again the integral of e to the alpha t is 1 over alpha e to the alpha t, so I get the limit as j pushes out to infinity of, let's see, the integral of e to the minus st becomes 1 over negative s, so I guess I'll just put the negative here and the s here, e to the minus st, and I'll evaluate that from 0 to j. So applying the evaluation theorem, let's see, I get the limit as j goes out to infinity, and here I'll have, let's say, negative 1 over s, and at the upper limit I have e to the minus sj. Minus a minus becomes a plus, let's say 1 over s, e to the 0, and e to the 0 of course is just 1, so that becomes a 1 over s. Now let's apply our limit. So if I take the limit as j goes out to infinity, well, I get this negative 1 over s, and just some value maybe, e to the minus sj, but as j gets very large, 1 over e to the j of course gets very, very small. So this term essentially drives to 0, and I'm just left with 1 over s. So for now, we have that the Laplace transform of 1 is just 1 over s. Likewise, we could have plugged in any constant, so the Laplace transform of any constant, we call it c, should be, since a constant doesn't change, we should end up with, if we just apply the definition, the integral from 0 to infinity e to the minus st times the constant dt, and since the constant can come out of the integral, we get c times the integral from 0 to infinity e to the minus st times 1 dt. And we've already established that this is just 1 over s, so this should become c times 1 over s. Okay, so the Laplace transform of a constant is the same as the constant times the Laplace transform of 1. And this is going to prove very important when we take inverse Laplace transforms, because we know that the inverse, say Laplace transform, just much like when we did with the derivative and the antiderivative of. So if the Laplace transform of 1 maps to 1 over s, seems likely that the inverse Laplace transform of 1 over s should map back to 1. Or if we have some constant, so if I have the inverse Laplace transform of some constant, say over s, I should be able to just factor out the constant times the inverse Laplace transform of 1 over s, and I should get the same thing. I should just get back the constant itself.